All right, welcome back, folks. This problem was created by yours truly, and I want you to sketch the velocity and acceleration graphs corresponding to example A in problem 9 from chapter 11. And once we have those graphs sketched, we're going to confirm their shapes based on conservation of energy and Newton's second law. So you can find in the book that example A in problem number 9 has this kind of shape. And what we're talking about is the motion of a mass connected to a spring. And this tells us the position as a function of time. So it has this oscillatory pattern. And in fact, I'll write this down because we're going to need it later, is that the position of this particle has some kind of amplitude. And it oscillates in time. Given the fact it starts at 0 and then it starts to grow, we know it must be the sine function. And the argument of the sine function has omega t. Okay, so just based on what we know about graphing and kinematics, we know that the velocity versus time graph is supposed to in some way tell us about the slope of the position versus time graph. And likewise, the acceleration graph should tell us about the slope of the velocity versus time graph. So I'm looking at the position graph, and it looks kind of complicated. It looks wiggly. But at least what we can do is we can figure out what the slope of this graph does at various points in time. So what I'll go ahead and point out is that at the very beginning, the slope is positive. And in fact, it continues to be positive, although it gets slightly less positive, until it gets to this point where it's definitely 0 at the top because it's flat. So if you like, I'll write here it's flat. In other words, 0 slope. Here it's positive. It's getting less and less positive. Later on, after you get to the flat part or the 0 slope section, then the slope starts becoming negative. So negative. It's negative. It gets even more negative to here. And then it gets a little less negative, little less negative. And then all of a sudden it goes to 0 again. So here we go. It's another 0. And then it becomes positive. So the general shape that we should have for the velocity versus time graph is something that apparently is positive at the beginning. So I'll just kind of sketch this out, starting off with some positive value. It gets less positive until it gets to 0 at 1 second. That's here. And then it starts going negative, okay? And then at about 3 seconds, it goes to 0 again. That's here. And then it starts going positive again. In between, at point 2, that's when it's most steep. I'm going to kind of estimate that to be about down here. And at point 4, it looks like it has kind of the same slope as at point 2 and the same slope as at the beginning, although it's not negative, it's positive. So if you like some number here, it's positive, the same number here but negative, the same number here but positive. So it looks like it's got that kind of shape. Positive to 0, negative, etc. It looks like it might actually be wiggly just like this graph. And if we kind of smooth it out, you might expect it to kind of start off and then go down through 0, get to the bottom, and then start turning up, going to positive, and flip around like that. So that's the general shape that the velocity versus time graph should have. You might want to think about this also in terms of the picture of what's going on. This is the big cinder block. This is a spring which holds the mass. The motion, as we know, goes back and forth. I'll just kind of write this out like this. And what we expect to happen is that when the mass on the spring is all the way at one end, it's gone as far as it can, so its x value might be very big, positive, or big, negative. But at that point, that's when its speed has come to 0, so the velocity graph should actually be 0, which it is. So that's consistent with what we expect. All right, using the same technique, again, going from x to v, we're just getting the slopes of this graph to tell us what this graph looks like. Going from v to a, we want to get the slopes of this graph as well. We can do the same trick. We notice at the beginning, it's basically flat. In other words, the slope here appears to be about 0. It goes negative here, so I'll just kind of indicate that. It starts to get negative, and it gets even more negative. And then it gets a little less negative until it gets to the bottom, at which point it's 0 again. And then it starts turning positive in this section. It's very positive here, and then it gets less positive until it goes back to 0. So if you start putting in these intermediate quantities or intermediate estimates, again, something that's basically 0 at the beginning, something negative later on at 1 second, going to 0 at 2 seconds, going to something positive at 3 seconds, and getting back to 0 at 4 seconds. Now, my artwork isn't very good, but I think you get the idea that if you smooth this out, it comes down, hits the bottom, turns around, goes up, gets to the top, turns around, goes down, and it looks wiggly. In fact, it looks wiggly almost in the sense that it's like the minus of this graph. It's like this graph flipped around. And that is something we can confirm. Okay, so let's see if we can confirm what these graphs should look like. I'm actually going to start with confirming what the acceleration graph looks like. So let's see. Confirm A as a function of time, the acceleration. The claim is that we can use Newton's second law to do this, so let's remind ourselves what that says. Newton's second law says the net force is equal to the mass times the acceleration. The net force in this equation is just provided by the spring force. That spring force, I'll just remind you, that spring force is equal to minus kx. It's minus, it's always pointing in the direction opposite to where the mass has gone. It's proportional to the spring constant k, and it depends on how far you've gone. So anyway, the net force is only provided by the spring force, which is minus kx, and that in fact is equal to mass times acceleration. So if you want to know what the acceleration is, all you have to do is divide by the mass. In other words, minus k over m times x, well, x has this general shape. A times the sine of omega t, that should be the general shape of our acceleration. It should have a sinusoidal kind of behavior, which it does. But given that this overall minus sign is there, that means it should look like the sine graph, but flipped upside down. So that confirms this graph. Lastly, let's confirm v, which takes a little bit more work. We're going to do this using conservation of energy. So let me remind you of a couple of things. The energy of this system, there's two types. One is there's kinetic energy because you have a massive object moving, and there's also potential energy stored in the spring. So altogether, the energy is equal to kinetic plus potential. And I'll remind you that since energy is conserved, what that means is that this total energy is also equal to whatever the energy is at when it's moving the fastest and when it's not displaced very far. In other words, this is equal to the same energy when all the energy is stored in kinetic and there's none in potential. And likewise, you can have all the energy stored in potential and none in kinetic. Okay? Using that fact, and good old kinetic energy is equal to 1/2 mv squared, and the potential energy, which is just the spring, 1/2 kx squared, that tells us that the maximum energy, potential energy, which is the total energy, should be equal to 1/2 k x max squared. And that maximum stretching distance is just a, right? Because sine can't be any bigger than 1 or -1, which means x can't be any farther from equilibrium than a or minus a. So this is 1/2 k a squared. All right, so what I'm trying to do is get to a relationship that will tell us something about v. That's hiding in here in the kinetic energy. So let's take this a step further. The kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. And all that is equal to 1/2 ka squared. And I want to use this equation to solve for v. All right, so let's see if we can make some progress by using this known function of the position. Writing this again, 1/2 mv squared plus 1/2 k, that x is that quantity squared, in other words, a squared, sine squared omega t. And all that is equal to 1/2 k a squared. We want to solve for v, so let's first take this to the other side, subtract it to the other side, giving us 1/2 mv squared equal to 1/2 k a squared minus 1/2 k a squared sine squared omega t. Now the fun thing happens where you notice that there's 1/2 k a squared in both terms. I think it's fun, you'll have to excuse me. 1/2 ka squared, I can factor that out, and what I'm left with is 1 minus sine squared omega t. And if I've been a professor that's on the ball, I would have given you a hint or a reminder about what this relationship is here, 1 minus sine squared. Or perhaps I would have reminded you, I'll put the tip up here, I would have reminded you that sine squared of any argument plus cosine squared of any argument is equal to 1. In other words, whenever you see 1 minus sine squared, you know that that must be the same as cosine squared. And now that you see the cosine squared, maybe you can see why this relationship here might actually work out, but let's finally confirm it. On the left-hand side, we have 1/2 mv squared. On the right-hand side, we have 1/2 ka squared. Let's cancel off the 1/2s and divide by m. So the second to last step is that v squared is equal to k over m a squared cosine squared omega t. And then finally, let's take a square root. V is apparently equal to square root of k over m times the amplitude times cosine omega t. And technically, there should be a plus or minus, so we're going to have to use the physics to decide whether it's plus or minus. Apparently, based on the fact that we know that if this is what the position looks like as a function of time, the velocity must start off as positive because, well, the slope of this is definitely positive, so we'll go with the positive sign. Lastly, I'll point out that square root of k over m should look familiar. That's just the angular frequency or angular speed. In other words, that's just omega, so the velocity here is actually just omega times a cosine omega t, having this basic cosine type structure, so you know you've done it right.